Greetings to all and welcome to this lecture. We are in module 5, lecture number 5, complete all reason model part 2. In this lecture, we will see how we will evaluate psi S0 and psi SL, which is nothing but the surface potential near the source and the surface potential near the drain. We will also see what is gradual channel approximation and how we are including in our model. These are the learning outcome of this lecture, which helps us to understand the incorporation of surface potential psi S0 and psi SL in the model what we have derived in previous lecture. We will also see that how we compute the drain current by applying the all reason model equation for different gate and drain voltages. Let us do a quick recap. We started our analysis by considering that the thickness of the inversion region is infinitesimal small. We said that at any position in x, so considering this is x direction and this is n plus source, this is n plus drain, this is x direction, this is p type body, oxide, gate, source, drain, and this is y direction. So along the x, at any point of x, the current is nothing but component of drift as well as diffusion. So Ix can be written as I drift plus I diffusion. Then the drift current is given as mu into W into minus Qi dash into d psi s by dx, where d psi s by dx is the horizontal electric field in this direction, which is the resultant of applied VdB or Vds. As we mentioned, this value is with respect to considering body as a reference, and this is with considering source as a reference. Similarly, the diffusion current component can be given as mu into W into phi t dqi dash by dx. By following these equation and putting in a general equation of Ids is equals to Ids1, we derive two components, that is Ids1 and Ids2. Here Ids1 can be given by W by L integration of mu into minus Qi dash between the limit of psi S0 and psi SL, where psi S0 is the surface potential at source channel junction or just here, and the surface potential at this point is given by psi SL. By keeping all these values and expressions in the final expression, we ultimately got the expression of Ids1 and Ids2. The only thing is left, which is to calculate psi SL and psi S0 in terms of Q dash and the applied voltage. It means, can I calculate the surface potential psi S0 or psi SL as a function of applied voltage, because I need to relate the surface potential and the inversion charge here inside the body with the terminal voltages. So to do that, again we will follow the potential balance equation. We have written this potential balance equation many a times, and we find that it can be written as V flat band voltage plus psi s minus Qc dash divided by Cox dash, where Qc dash is nothing but the channel charge. Following the module number 2, we have derived the channel charge, which is nothing but minus of signum of psi s into square root of 2q Na into epsilon s into phi t e to the power of minus psi s by phi t plus psi s minus phi t plus e to the power of minus 2 phi f by phi t into e to the power of psi s by phi t into phi t minus psi s minus phi t. This expression we have derived in module number 2 when we were saying that in the channel we do have a contribution of electrons, we do have a contribution of holes, and immobile ions. Remember, this is the contribution of holes and this is the contribution came by immobile ions. We have used the same formula in 3-terminal MOS structure, considering that the terminal voltage VCB came into picture by the contribution of electron, and hence this formula can be rewritten as 2 phi f plus VCB. So, following these previous expressions, we can use QC dash for inversion and depletion and ignoring the whole contribution. Further, we are replacing VCB by VSB to write the expression of surface potential psi S0, and we replace VCB by VDB to write the expression for psi SL. So, ultimately QC dash can be written as minus 2 into Q into Na into epsilon S into psi S plus e to the power of psi S minus 2 phi f plus VSB over phi t into phi t, where if I want to rewrite the expression in terms of psi S0, I will put psi S0 here and I will put this equation of QC dash here. So, I will get a form of psi S0 and psi SL, where psi S0 is nothing but, from here psi S0 is nothing but VGB minus V flat band voltage minus Cox dash into minus 2 into Q into Na into epsilon S divided by Cox dash. This quantity is all well defined as gamma. So, ultimately you will get an expression that VGB minus V flat band voltage minus gamma times of psi S0 plus phi t e to the power of psi S0 minus 2 phi f minus VSB y phi t. So, when we are talking about the surface potential near source channel junction, we are taking VSB because it is influenced by this voltage. Similarly, when we are talking about VDB, then we are writing psi SL. So, this expression can be solved in two ways. Either we can use iterative numerical approach by solving first and second order Newton-Raphson schemes, or we can follow the analytical approximation. The good way in analytical approximation is to assume the reasonable value of psi s between psi S0 and psi SL, solve the expression and then use some smoothing function to get the converged output. Make sure the computation time and numerical robustness should be good enough while using these approaches. To move further, we have seen the final expression of psi S0 and psi SL can be given by this, where the surface potential of psi S0 and psi SL is defined at this point. Again, we can strictly mention that we are ignoring the edge effect. What the edge effect means, the potential at n plus region and the potential at the channel is different because of this depletion region. If you see, the potential here is different than the potential here because there is a depletion region coming into picture. We are considering the expansion of this depletion region between n plus and p is same as the expansion near the body. It means here the expansion and here the expansion will be same. So, this region causes edge effect. What it means is, in this region the electric field is not one directional. We cannot say the electric field is only exist in this direction, or we cannot say the electric field is only vertical. So, we need to use 2D Poisson equation to solve this equation, and this is actually violates our gradual channel approximation. So, to follow the gradual channel approximation, we need to ignore the edge effect. So, to ignore the edge effect, we can simply say whatever be the effects coming here and what are the effects coming here. If we want to ignore can we rewrite the surface potential in terms of psi SL and psi S0? So, this surface potential carries some edge effect. Similarly, this surface potential carries some edge effect. Considering the symmetricity of the structure, those edge effects get cancelled, but when we are writing the surface potential in terms of psi SL minus psi S0. Interestingly, if you see in the current equation of IDS1 and IDS2, we can get the psi SL minus psi S0 terms common. Let us analyze the equation number 1 for IDS1. If you see here, I can take out psi SL minus psi S0 from here. Similarly, this can be written as a square minus b square can be written as a plus b into a minus b. So, you can take psi SL plus psi S0 into psi SL minus psi S0. So, you can take this term out, you can take this term out. Now, here this is in the form of a cube minus b cube, which can be written as a minus b into a square plus ab plus b square. Here a is psi S L to the power 1 by 2 and b is psi S 0 to the power 1 by 2. So, this can be written as psi S L plus psi S L to the power 1 by 2 psi S 0 to the power 1 by 2 plus psi S 0 to the power 1 by 2 whole square, meaning psi S 0. So, if I want to take psi S L minus psi S 0, I will multiply in the numerator and denominator by psi S L to the power 1 by 2 plus psi S 0 to the power 1 by 2. If I do a multiplication, this is nothing but a plus b into a minus b. So, the numerator will get psi S L minus psi S 0, and in the denominator you need to multiply with the same factor psi S L to the power 1 by 2 plus psi S 0 to the power 1 by 2. So, in the equation of IDS1, if you are taking out psi SL minus psi S0, you will ultimately get VGB minus V flatman voltage minus half of psi SL plus psi S0 as I mentioned here, minus 2 by 3 gamma into psi SL to the power of 1, or you can simply write psi SL plus psi SL to the power 1 by 2 psi S0 to the power 1 by 2, and this will be plus, this will be plus psi S0. Now, divided by psi SL to the power 1 by 2 plus psi S0 to the power 1 by 2. Now, let us analyze IDS2. Again, if you want to take out psi SL minus psi S0 from this equation, this is taken out and this can be written as psi SL to the power 1 by 2 minus psi SL to the psi S0 to the power 1 by 2, multiply and divide by psi SL to the power 1 by 2 plus psi S0 to the power 1 by 2. So, in the numerator you will get a minus b into a plus b, and hence you can take out this psi SL minus psi S0 and you will left with phi t plus phi t into gamma divided by this factor. If we closely look into it, by taking this psi SL minus psi S0, we are ultimately ignoring or neglecting the edge effect. Further, we can see this equation as follows. You do have some expression or some function which is a function of VGB. Yes, obviously it is affected by VDS and or VDB and VSB, but you have another term which is psi SL minus psi S0, meaning the difference between the surface potential at this side and this side. This difference is nothing but what causes a horizontal field which is responsible for the carrier to flow. Here VGB is responsible to causes inversion. You remember our analogy of fluid dynamics. We said that when we turn on the piston or when we open the piston, there will be a transfer of water from source to drain. So, the role of piston or the role of gate is to create inversion, and The role of VDS is to change the level of source and drain tank such that the carrier or water flows. That is what this is causing a horizontal field. Horizontal field, and this is actually a function of vertical field. What we assume is gradual channel approximation, considering the length is very large and hence Ex is very small compared to Ey. So let us see further what will happen when you increase the drain to body voltage or drain to source voltage. Again, to give you a clear picture, let me derive the schematic. N plus here, N plus here, and you are increasing VDB voltage. Let us consider VGB is constant. And we will analyze how my surface potential is changes. For example, here the surface potential is psi S0 and here the surface potential is psi SL. Let me increase VDB value. If I increase the VDB value, I know that the inversion region at this edge will go from strong to moderate to weak. Ultimately, the surface potential is increases and get pinned to a maximum value of surface potential, that is psi SA. Why we are saying it is a maximum value? For example, you applied a VGB, then there is a depletion. Consider you have applied VGB small enough, so there is not inversion started. If you are in depletion, there is some voltage drop here to support this depletion layer. This voltage is nothing but psi S0. Similarly, here also there is a surface potential which is psi SL to support this depletion layer. Now, when you increase VGB, ultimately the inversion charge carriers comes in, and we know across the inversion charge the drop is considered as to be small, such that all the potential is dropped across depletion region. Now, let us assume that you are in inversion and now you are increasing VDB. The moment you increase VDB, the inversion layer near the drain end will be vanished, because you are increasing VDB and you are moving from strong inversion to weak inversion. The moment you increase the VDB, this region is go in weak inversion, and hence the surface potential attains to its maximum value of psi SA, which is nothing but obtained in depletion and weak inversion. But here the surface potential is its minimum value, and hence you will get a difference of psi SL minus psi S0, which is responsible to cause a voltage difference in the channel, which is responsible to causes a current to flow. Again, these values can be marked already in previous lectures, where we found that the increase in VDB moves your channel charge or region of operation from strong inversion to weak inversion. Okay. Now, here the psi SA is considered to be a maximum voltage drop across the channel at depletion or weak inversion. Now, let us analyze the output characteristic of a MOS transistor thoroughly. Let us consider that in a schematic we are considering VDB is exactly equals to VSB. This is gate, this is body, this is drain, and this is source side. Now, let us consider we are assuming that VDB is equals to VSB, and you applied VGB in such a way that you are in strong inversion, meaning when you apply VGB, ultimately the depletion charge comes into picture. After depletion, there is an inversion electrons like this, but there is no flow of electron because we have considered VDB is equals to VSB. Now, what will happen if you rise VDB over VSB? When you increase VDB, ultimately the surface potential here follows the previous trend what we have discussed, because when you increase VDB, ultimately the surface potential is increasing. The increase in surface potential over the surface potential of psi S0 is causing a horizontal field, that is psi SL minus psi S0, which is responsible to attract the electron toward the drain side. This is corresponds to the onset of channel potential curvature and making non-saturation of the device. It means you are in linear region, the current is increases like this. Now let us consider you are increasing VDB beyond a point, and then the surface potential is pinned to a value of psi SA, which is a function of VGB. So this potential is get pinned. Now even if you increase VDB, ultimately this potential is not changing, the psi SL is not changing. If this is not changing, the current equation which we derived is directly proportional to psi SL minus psi S0. So by increasing VDS also, this potential is not changing, meaning the difference is get fixed, and hence the current is constant. That is what you called a saturation region of operation, where VDB is increased beyond a point where the surface potential is pinned to a value of psi SA. As we know that this psi SA is a function of VGB, it means if we really want more current, then we need to increase VGB. If we increase VGB, the surface potential is increases and the saturation point will also get shift, and the amount of the current is also increasing. Let us analyze again for a constant VGB. So you applied a constant VGB and you have a channel like this. When you increase VDB, the channel here is going from saturation to weak inversion, but this side of the channel having electrons. So the region of operation, as we have discussed in previous lecture, is can be defined by heavily doped or heavily inverted side of the channel, which we called it as we are in strong inversion, even though this side of the channel is weakly inverted. So the carrier will move from this side to this side, right, and this gives rise to a current which is saturation. Now when you increase VGB, ultimately you are increasing the potential here. If the potential is increasing, this causes more electrons to be available here, and hence the current will increase like this, and the saturation point will also get shifted at the right hand side, because you need to apply more VDB to make it weakly inverted or depleted. Here if we plot this output characteristic with respect to VDB, then we need to consider VSB, because here body is a reference point, but if we plot the characteristic with respect to VDS, then this is just shifted to 0 and we will get a output characteristic like this, which is IDS versus VDS, right. This is the curve given for different values of VSB. In the previous analysis, we said that we are keeping VSB constant, we are not changing VSB, and all the analysis we have checked that what will happen when VDB is changed. So this is N plus, this is N plus. We found that when you increase the VDB, ultimately this region got changed from strong inversion to weak inversion to depletion, and the region of operation is defined by this side, and we say that we are still in strong inversion. But what will happen if you increase VSB? The same operation happens here at the source channel junction, where the increase in VSB increases the surface potential like this, and maybe you are entering from strong inversion to moderate inversion. If you are going from strong inversion to moderate inversion, the amount of charge in the channel will be less, and that is what you are seeing, the amount of the current is degraded. Here the range of the current is this much when VSB is 0. When you are applying source to body voltage of some amount, then the range of the current is getting degraded because the total charge available near the channel is degraded. This can be restored by applying the VGB again, right. Let us analyze the transfer characteristic. In general, the transfer characteristic is plotted between IDS, the current, output current with respect to input voltage or the gate voltage. Let us consider the value of VDB in such a way that the drain side end is in weak inversion and you are in strong inversion at the source side. So, this potential is psi s 0, this potential is psi s L, right, and this is VGB. Let us analyze the transfer characteristic of the MOS transistor. In general, the transfer characteristic of the MOS transistor is plotted between IDS and VGB. So, here let us consider we do have a schematic of MOS transistor N plus, and this is gate voltage, this is source voltage and this is drain, where you are applying VDB and here you are applying VSB. Let us consider we are plotting this graph for a fixed value of VDB, where VDB is such that you are in weak inversion or depletion at drain side. Now you vary VGB. If you increase VGB with a very small value, what will happen? There is a depletion first at the source side and then a weakly inverted carriers are available. So, this region is in weak inversion, this region is in weak inversion, and you say that you are in weak inversion of operation. That is what mentioned here. This is weak inversion itself because you designed or you fixed the value of VDB, but based on VGB value this is in weak inversion now. The VGB is small enough such that there is no inversion charge or a few amount of inversion charge available. So, you are in weak inversion because both end are in weak inversion. In weak inversion, the surface potential here is psi s 0, which is nothing but psi s a. Similarly, at this edge is meant to be weak inversion, so psi s l is nothing but psi s a. If you see carefully, the difference between psi s l and psi s 0 is almost 0, meaning there is no electric field exists which pulls the electron from source to drain, and you can say there is no drift component. However, if you increase a small amount of VGB, there are carriers available at the source side. The concentration gradient exists in the channel. Here there are more carriers, here there are less carrier, and hence there is a diffusion current because the electrons will move from higher concentration to lower concentration. So that in the weak inversion of operation we found that IDS 2 will dominate, that is diffusion current will dominate. Let us consider you increase the VGB in such a way that more number of inversion charge carrier available here near the source. So, this side is now heavily inverted, or you can say strongly inverted, or you are in strong inversion. In this condition also, this region is in weakly inversion. This region is weakly inverted, meaning the total operation can be defined as strongly inverted because one side of the channel is heavily inverted and one side of the channel is weakly inverted. The region of operation can be defined by the heavily inverted side. So, you are in strong inversion. At that moment, if you see, the surface potential here psi s l is fixed to psi s a, which is maximum value, whereas because of the strong inversion, the surface potential at the source channel junction is now reduced to some value of psi s 0. So, you can follow this graph of psi s a versus VCB or VSB, and you are actually inverting VGB such that the surface potential is lower than the psi s a. So there is a significant difference between this potentials comes up. Here psi SL is the maximum surface potential at this side, whereas by increasing VGB the inversion charge forms up and hence the surface potential decreases below psi SA. So you will get a significant amount of difference which causes drift component to come into picture. That is what in strong inversion IDS1 dominates, which is nothing but a drift component of the current. That is what if you plot the complete equation of IDS comprising IDS1 and IDS2, we can easily see that in the strong inversion IDS2 is dominating, whereas in weak inversion IDS2 is dominating. However, in moderate inversion both the current expression can be dominate, in the sense we need to follow a closed form equation and precisely model the weak inversion region of operation. That is what we have already discussed in previous lectures. The modeling in moderate inversion is bit more difficult because the charge and surface potential does not follow a prescribed rule, whether it is in linear or exponential. So we need to use a complete closed form equation of QC dash. So let me summarize this lecture. In this lecture we found that the total drain current can be expressed as a sum of drift and diffusion component representing the charge transport due to electric field and carrier concentration. We also found how to calculate the surface potential psi S0 and psi SL, which is nothing but the surface potential measured near the source channel junction and near the channel drain junction. We saw that the exponential term in the equation represent the minority carrier concentration, which comes under weak inversion, or in weak inversion the current is dominated by diffusion, whereas in strong inversion the current is dominated by drift. So we will stop here for today. Until then, take care.